All right. Let me know if you don't have them. Otherwise, let's begin. So today's lesson, this entire unit, is focusing on polynomial functions. Now, the good news is that you guys already learned quite a bit about polynomial functions. All of the linear functions you have over a graph, those are polynomials. All of the quadratics, those are polynomials. The cubics, little experience we've had with those are polynomials. So we're going to be talking about all kinds of polynomials, and we're going to be able to factor all kinds of polynomials. So first, the graph of a polynomial function is both smooth and continuous. So kind of based on your experience, you know, they're smooth, they kind of look like that. That would be like a cubic function. And they're continuous, which means you don't have to lift up your pencil at all to graph them. A polynomial of degree n, where n is a non-negative integer, is a function defined by this expression, f of x equals all of that. Now that's just fancy language, fancy math language, basically saying if you have a polynomial, the exponent has to be an integer, right? Like 3 and 2 and 1. It can't be negative, right? And that's what that non-negative means. And it can't be a fraction. So all this language here, this, and this, that's just fancy language for notation. The linear factor of a polynomial is this. So linear factored form is going to be something that we're going to do this year or this unit. And linear factors are written like this. And we're going to be able to factor, I know we have experience in factoring quadratics, but we're going to be able to factor all kinds of linear factors. So, for example, y equals 3 times x minus 1 squared times x plus 4 times x plus minus 7 cubed, right? So that would be something we call linear factored form. No variable in the denominator, under the radical, or in the exponent. So these are some of the criteria when you're determining whether something is a linear factor. Okay, so it has to have all those things. The coefficients can be any real number. So the coefficients are the number that you guys would say like, oh, it's the number of the variable, right? But it's not in front of technically. It's a so like for instance, like 3x or 1/3 x or even pi x. Those are examples of coefficients that would be totally fine. All right, degree. This is something that I don't know how much experience you have with that. The degree is the highest power of the polynomial in standard form. Okay, so it's the biggest exponent. And when it's in standard form, it's going to look something like this. And regardless of how many other exponents come after the biggest one, we would say the degree of this is degree 5. So it doesn't matter what comes afterwards. We're looking for the biggest exponent, and that gives us our degree. Now, if it's in linear factored form, then we add the exponents. So what that looks like, and students oftentimes confuse the two of these, so we got to make sure this is clear. So linear factored form, which looks something like this. So if it's in linear factored form, it's factored out with linear factors like x minus 1 and x plus 3. Those are linear factors. And the way we find a degree with that is we would have to add these exponents together, and this would also be a degree 5. Now, this is something that you could do. I don't recommend it because it'd be a lot of work. You could multiply these out, expand them, multiply it all out, and you can find a degree that way. And when you multiply it out, you actually change it to standard form. But, and to go from, you can also go from standard form to linear factored form if you knew how to factor this, right? But, regardless of what form it is, you just got, you have your notes, you just got to kind of pay attention. If it's in standard form, you look for the biggest exponent. If it's in linear factored form, you have to add the exponents of the linear factors, right? So that's just something, again, something new. You got to study, you got to prepare for it. The term with the highest power on it, x, so an to the x, is called the leading term. And the idea behind it is it's not always going to be in front, because I know the word leading you typically think of as in front. You got to look for the biggest exponent. Okay, and that's going to tell you what your lead term is. The coefficient part of the lead term is called the leading coefficient. Well, that makes sense. All right, now, linear factors are just polynomials of degree 1. So the linear factors, the things you guys have been doing since junior high, those are polynomial factors of degree 1. So like, for instance, f of x equals 2x plus 7. We know that this is a line, has a slope of 2, a y-intercept of 7. It's still a polynomial, but it's just of degree 1, but we never really write that 1 there, but it's there. Just like this, constant functions are just polynomials of degree 0. So like f of x equals 4, or in other words, y equals 4. Well, that's, believe it or not, that's still a polynomial of degree 0. And that's because if you were to write it, it would be x to the 0 power. And hopefully we know that x to the 0 power, or anything to the 0 power, is just 1. So again, it's something that you never see. It's never written that way, but it's there, and it's degree 0. And this is something that, like after today, y'all never mention this again. But f of x equals 0 is called a 0 polynomial, and it has no degree. So that's just like y equals 0, which is just the x-axis. All right, so we're gonna, in normal times, I would have you guys, we'll do one of these and I have you guys try the rest, and then we'll share with the class. It's hard to do this virtually, but I do want to give you guys time to try it on your own to see if you actually understand it. So we're going to do these first two together. So the first question is it a polynomial function? Not just a function, a polynomial function. So the first one, f of x equals 3x to the 4th minus 15x to the 6th plus 1, it's definitely a polynomial function. The degree is 6, because I have to find the biggest exponent. Even though 4 is in front, technically the biggest exponent is the degree. The leading term is negative 15x to the 6th, and the leading coefficient is negative 15. But now for g of x, this is not a polynomial function because of the root 3x, because we have a variable under a radical, and that violates the function definition, or the polynomial function definition. So you don't have to worry about the rest of these. So with the remaining 5, there's 3 yeses and 2 nos. So I want you guys to see if you could figure out the rest of them. I'm gonna give you like a minute to try it on your own, and then we'll go over it. So I want to see if what you guys can do on your own. Okay, let's see how we did. All right, so the first one is a yes. That pi is that's a real number, so it doesn't change anything there. The degree is 5. The leading term is negative pi x to the 5th. The lead coefficient is negative pi. The next one is a yes. This square root of 5, that's fine. That's a real number, but there's no variable underneath the radical, so we're safe. So now the degree is 3. The lead term is negative 5x cubed. And the lead coefficient is negative 5. K of x, it's a yes. I know we see a 4 in the denominator, but that's okay. You just can't have a variable in the denominator. But now this is where it gets a little tricky. The degree is 2. The leading term, that's the hard part. So we had to expand this so you could kind of see the whole story here. So this is really 2 over 4 minus 1 over 4x squared. So my leading term is actually negative 1/4 x squared. And my lead coefficient is negative 1/4. All right, now the last two, by process of elimination, you know that those are no's. And here's why. We have a variable in the denominator. And this is a no because we have a non-integer exponent. Okay, and those are the two no-nos. So that goes out. All right, so now power functions. So the idea behind a power function is it's a taking a polynomial and expanding it way out so that you're zooming like as much as you could zoom. So like for example, if I have the equation f of x equals 3x to the 5th minus 4x cubed plus 5x minus 7, you know, if you graph that, it's going to have a whole bunch of like humps and it's going to look kind of funky in the middle. But at the end of the day, if you zoom out, it looks like 3x to the 5th. So the end behavior or the power function is what it looks like at its most basic core, right? And what it looks like as you go to negative infinity, as you go to positive infinity. So a power function of the degree n is a monomial function, which is a single term, like 3x to the 5th, of the form f of x equals ax to the n, where a is a real number, a can't equal 0, and n is greater than 0. That's our polynomial definition. So we're going to be looking at using power functions to help us get a better idea of what the actual graph looks like. So we're going to do rough sketches here of these. And really the only pattern is that as the exponent gets larger, the graph gets tighter and tighter, or narrower and narrower, okay? So x squared kind of looks like this. We know that. Negative x squared, x to the 4th, a little narrower. Negative x to the 4th. X to the 6th is even more narrower. And the reason why it's so narrow, if you think about it, you know, for all of these, the 3 points they're going to have in common are 0, 0, negative 1, 1, 1, 1. But as you get larger and larger, for example, 2 squared is 4, 2 to the 4th is 16, and 2 to the 6th is like 216. So that's why the graphs get narrower and narrower and narrower, because as you go further for the x value, it's going to shoot straight up, right? Likewise, y equals x, that's the original mother function graph, probably the first graph we learned. Negative x cubed, negative x cubed, x to the 5th, negative x to the 5th. All right, so now we're going to use these rough sketches to help us identify these. So we can separate our graphs into two separate kinds of categories: even power functions and odd power functions. So when we talked about the words even and odd, we're talking about the exponents. And the even power functions out of our graphs right here are a through f. And the odd power functions are the graphs g through l. So we're going to kind of dissect everything here and try to get a good understanding of these even and odd power functions. So symmetry. Well, if you look at our even power functions, they're all symmetrical with respect to the y-axis. So for symmetry, we say the y-axis. Now for the odd power functions, I know you might be thinking x-axis, but no, it's not. They have a different kind of symmetry. We call it origin symmetry, which basically means the points are kind of switched. So 1, 1 goes to negative 1, 1. Okay, negative 1, 1 goes to positive 1, negative 1. Here, like 2, 8 would go to negative 2, negative 8, right? So this is that symmetry relationship with the origin, right? So the idea behind it is you kind of switch the signs, and if you continue that pattern, you'll be able to show symmetry to the origin. So the y-axis, and this is origin. All right, the easy part is the domain. For both of these, for all polynomial functions, the domain is all real numbers. So that's never going to be an issue that you have to worry about. Now, range. Okay, let's do a little discovery here. So the range, when your a value is greater than 0, or in other words, positive, and the range when your a value is less than 0, or in other words, negative. So let's take a look at the even functions for now. So when the a value is 0, we're talking about a, c, and e. And we said the domain was all reals, but their range, well, that's a little different. So if you look at these, a, c, and e, we know that the pointing up to infinity, but what's the lowest point? And that's how we find the range. It's bracket. First, they look like this. So the range would be bracket lowest y value to infinity. And when a is negative, which looks like this, the arrows are pointing down to infinity, so that's where we start from negative infinity to the biggest y value. Bracket. Now the easy part is the odd functions. Those are going to be both negative infinity to infinity. So it doesn't matter if it's positive or negative for the a values, because if you look at all these graphs, they go from negative infinity to positive infinity, regardless of the sign, whether it's negative or positive. So that's the nice thing about odd power functions. You don't have to worry about them too much. All right, end behavior. This is going to be our first kind of taste into calculus here. We're going to be talking about things called limits. And our end behavior is, again, this idea of as you zoom out, or as you go to negative infinity and positive infinity, as you get really, really far up, where does a graph approach? Is it going up? Is it going down? As you go to the left, as you go to the right, does your graph go up or down, right? And so, again, end behavior when a is greater than 0, or when it's positive. And again, we have to get used to this notation. So as x goes to negative infinity, or in other words, as your graph goes to the left, as x goes to the left, where does your graph go? Well, it's always helpful to have a little sketch here. So I'm going to do this for all of these. And we're making, kind of a big generalization, but this is going to be, it's going to be a pattern that works every single time. So looking at this as our helpful sketch, and this sketch applies to all even power functions. As your graph goes to the left, okay, and again, we're looking at A, C, and E, as it goes to the left, your graph goes up, or in other words, y goes to infinity. So as x goes to negative infinity, y goes up to positive infinity. But we don't use the words up and down, we use the words infinity and negative infinity. So depending on the context, negative infinity could mean left, but it also could mean down, and positive infinity could mean right, and it also could mean up, depending if we're saying x or y. So again, the question, the setup is as x goes to infinity, or in other words, as your graph goes to the right, what happens to your graph in terms of the up and down direction? Well, this too goes to infinity or up. All right, again, we don't use up and down, but I want you guys to, we're still learning this, so I want you to get used to that, okay? All right, so let's take a look at the odd function. So as x goes to negative infinity, or as it goes to the left, where is our graph going? Well, it's pointing down, right? But we say negative infinity. And as x goes to positive infinity, or to the right, where does our graph go? Well, the arrow's pointing up, so the graph goes to positive infinity. All right, so now same thing here, end behavior, but when your a value is negative. So it kind of looks like this. And again, left and right. So as our graph goes to the left, as x goes to the left, our graph goes down. So we say y goes to negative infinity. And as our graph goes to the right, y still goes down. So we say y goes to negative infinity. And here again, as x goes to the left, as x goes to negative infinity, my graph goes up. So y goes to positive infinity. And as x goes to the right, my graph goes down to negative infinity. Okay, and again, this is not something to memorize. You could easily just put any equation in the graphic calculator or the power function in the graphic calculator, and you'll get a really good idea of what this looks like. All right, we'll take a mini break after this to kind of stretch our legs. You know, get out if you guys are like laying in your bed doing notes, just to kind of stretch out. All right, so end behavior. For large values of x, large values of the absolute value of x. And the reason I had to say this is because we're saying large negative values and large positive values. So as x gets really, really, really small, or as x gets really, really, really large, the graph of polynomial function will behave like its leading term, y equals a sub n to the times x to the n. This is your power function. But secretly, it's just the lead term. And by identifying that lead term or the power function, you pretty much know what the end behavior is going to look like. Okay, so consider the end behavior of even and odd power functions when determining the end behavior of the polynomial. Okay, so basically it's saying, you know, yeah, we can have this like really long polynomial, but at the end of the day, it's going to look just like its lead term at the end, right? At the end behavior for very large and very small values of x. So looking at this first one here, the end behavior is going to look like y equals negative 3x to the fifth, because that's the lead term. And I could go back up, and again, you guys have access to your notes, right, at any time. So I can go up and see what it looks like, all right? So negative 3x to the fifth, all right, well, that's going to look like L, right? And so I kind of know that it's going to look like this. And so to answer these questions, and I really think that, like the sketch here, that helps. So I would do a sketch for all of these. Okay, so now to answer these questions, now I'm really getting into my calculus notation. This LIM stands for the limit. So the limit of my function f of x as x goes to negative infinity. Or in other words, as x goes to the left, where is my graph going? Where is f of x going? Is it going up or is it going down? So looking at this sketch for help, as x goes to the left, f of x goes to positive infinity. It goes up. And again, what this means is the limit of f of x as x goes to negative infinity. So this means as your graph goes to the right, as x goes to the right, where is f of x going? And looking at our graph, it points down. So we say f of x goes to negative infinity, or in other words, down. All right, so take like a minute. I want to see, try these on your own. Again, I know that you guys could just wait till I post it, but challenge yourself and see if you really understand it. Okay, try these on your own and let's see how we did. All right. So I'm going to bet that everyone got the end behavior correct. So y equals 4x to the fourth, y equals 2x cubed, y equals negative 6x to the sixth. And like I said, a good strategy, if you need to, you can go back up here and look, but a good strategy is to go ahead and just make a rough sketch. So 4x to the fourth looks something like this at the end of the day. 2x cubed looks something like this at the end of the day. And negative 6x to the sixth will look something like this at the end of the day. All right, so as the end behavior goes on, that's a rough sketch of what they look like. So now we have to find out, okay, let's interpret what this means. So as x goes to the left, where does f of x go? Well, as this graph goes to the left, f of x goes to infinity. As it goes to the right, f of x still goes to infinity. Okay, looking at the next one. As your graph goes to the left, where does f of x go to? So as x goes to negative infinity, f of x also goes to negative infinity. And as f of x goes to positive infinity, or as x goes to positive infinity, f of x also goes to positive infinity. And the last one, as x goes to negative infinity, as your graph goes to the left, where does f of x go? Well, f of x goes to negative infinity. It's pointing down. And as x goes to the right, where does f of x go? It also goes to negative infinity because it's pointing down. All right, so kind of give me a thumbs up. How many guys got those three? Okay. Good. All right, very good. All right, so take a little break after this, but we'll end before a break. Our old friends, our transformations. So, you guys just took a test in this. I haven't graded them yet. I'm going to grade them tomorrow. Hoping you guys did really well on it. So, x minus 7. It's in the parentheses. So this is a shift right 7. Remember, it's counterintuitive. X to the fourth plus 8. That's outside the parentheses. So that's up 8. And 6x to the fourth. That's outside the parentheses. And we're multiplying it, which tells us it's a vertical stretch. Okay, x to the fifth minus 14. That's outside the parentheses. That's down 14. X plus 21 to the fifth. That's inside the parentheses. So that's going to be left 21, right? Counterintuitive. And lastly, there's two things going on here. Negative 1/2 x to the fifth. We have the negative that we have to honor first. So that's a reflection over the x-axis. And the 1/2, well, since it's less than 1, we say that it is a vertical compression. All right, so a little stretch break. Charge my pen because it keeps running out of juice. So let's take a 2-minute stretch break, walking around break. Oh. Oh.
Mr. Bassler,
Yes.
can you go back to the first page, please?
Mm-hmm. Okay. All right, so x-intercepts, real zeros. So they say real zeros because there are imaginary zeros or zeros that don't cross the x-axis. And we'll find those, that'll be the last thing we do. The real zeros are the ones that even if they're complex, or sorry, not complex, even if they're irrational, they still cross the x-axis or they touch the x-axis. And the way we determine that is something we call behavior of a polynomial at its x-intercepts depends on the multiplicity of its linear factors. So this idea of multiplicity is just basically looking at the exponents of the linear factors. So linear factors, remember, are when we put into factored form, and you could have repeating linear factors, and we've seen this. You know, when we have, for example, x minus 1 squared, right? That's a linear factor, and then we would say the multiplicity is 2 or even. So we've seen this before, but now we're going to expand it to all sizes of polynomials. So let's kind of get a feeling of what does it mean for multiplicity. So if there's even multiplicity, it touches it at the x-intercept. So for example, our example here, x minus 1 squared, that has even multiplicity, and we know this because we've already experienced graphing this, we know that it would look something like this. It crosses it at, it touches at 1, 0. So that is what we call a touch, which means it doesn't go through, doesn't cross the x-axis, it touches it at that point 1, 0. And the reason it does that is because it has even multiplicity. Okay, now there's things called odd multiplicity, and we've also seen those. So for example, if I have y equals x minus 1 times x plus 2, we know that it crosses the x-axis at positive 1 and negative 2. and it would look something like this. And we say it crosses at the x-axis, and we say it has odd multiplicity because, believe it or not, those are raised to the first power. Now we're going to go beyond quadratics. So we're going to look at polynomials that have degree 5, degree 6, degree 7. But our knowledge of polynomial, or our knowledge of parallelograms, parabolas, are going to be helpful here. So initiating the graphs below, an x-intercept is at 5, 0. What do you know about the multiplicity of the 0 at 5 and the factor x minus 5 for each of the corresponding polynomial functions? Okay, so these are screenshots of examples of crossing and touching. So this is a perfect example of a touch. What a touch means is it doesn't go through the x-axis. Now what it tells us is that it has even multiplicity. So this could be x minus 5 squared. It could be x minus 5 to the 4th. It could be x minus 5 to the 6th. Okay, but we know for sure it's even. Now, what both of these tell us is odd multiplicity. And we know because it crosses. Cross means that it goes through the x-axis, right? So now these could be x minus 5 to the 1st. It could be x minus 5 to the 3rd. It could be x minus 5 to the 7th, okay? But for sure, it's going to have an odd exponent on its linear factors. And again, the reason we know this is because it crosses the x-axis. So we're going to have to pay attention to, and this goes back and forth. So we can predict if it crosses, but also if it crosses, then we know for sure it's odd, right? The same thing with touches. If it touches, we know it's even, and if it's even, we know it's going to touch. So we're going to apply these. Now, the big idea, the reason why we're studying this is because we rely a lot on our graphic calculators, but you could learn a lot about a graph or the equation without a graphic calculator, just based on end behavior and touching and crossing zeros. Okay, so let's get a feel for this. So the degree, we're going to find the degree, the x-intercepts, the multiplicity of each zero, and describe whether the graph will cross or touch at each zero. So the degree is going to be our first challenge. Now, these are all in linear factored form, which means, going back to the first page, the sum of the exponents of each factor of a polynomial in linear factored form. So if I'm going to find a degree, I need to add the exponents. So looking at our problem here, there's an exponent of 2 and an exponent of 3, so my degree is 5. Now my x-intercepts, remember it's always the opposite of these numbers here. So I have 2 x-intercepts, one at 2, 0, the other at negative 7, 0. Multiplicity is based on the exponent. So the multiplicity of this one is even. The multiplicity of the 7 is odd. When we first do this, especially if students like half paying attention, they think like, oh, I get it. It's because the 2 is even and the 7 is odd. No, it has nothing to do with that. Okay? It has everything to do with the exponent. So multiplicity is looking at the exponents, not the actual value of the 0. Okay? Now, crossing or touching, that's dependent on even and odd. So if it's even, I know for sure it's a touch. And if it's odd, I know for sure it's a cross. Right? Now, check this out. I know you think I'm crazy that I said that you graph this without a calculator, but you could graph this without a calculator pretty, somewhat accurately. Check this out. I know that the end behavior is degree 5, so I know that it's going to go, as it goes to the right, it goes up to infinity, and it goes to the left, it goes down to negative infinity. okay? That's from the degree, I could tell this. Now, I also know, based on the multiplicity, that at 2, 0, it's gonna touch, and at -7, 0, it's gonna cross. The other thing I know, and this is a little harder to explain, but I know that the y-intercept is going to be very large. And the reason I know this is because I could put 0 in for x and 0 in for x here, and this is going to be -2 squared, which is +4, times 7 to the third power, which is 243. So it's going to be 4 times 243, which is large, right? And so I know with pretty good certainty, the graph is going to look something like this. Now check this out. I did this first block, so I kind of cheated, but it worked out. I'm not making this stuff up. You could do it without a calculator. I'll do it scratch for you guys, okay? So y minus 2 squared times, go back. Fresh start here. The graph's too big. There we go. All right, y equals parentheses x minus 2 squared parentheses x plus 7 cubed. Okay, there's my -7. There's my +2. Okay, see how it's going down the end behavior on the left, and whoops. And if I go up, see my y-intercept is up there. It's 4 times 243. But look at the end behavior. The line is shooting straight up after it hits the 2. Okay, so right here, it crosses somewhere around here, and then it hits the 2 and it goes up. So that graph that I made here, it's not that far off. Yes, there's details that I'm missing, but based on just this information, I have a good idea what the graph looks like. Let's try this again. So a lot of students forget about this. It's x to the first power, and it's also x minus 2 to the first power. So my degree here is 5. So it's 1 plus 3 plus 1. My x-intercepts are 0, -1, and +2. My multiplicity is odd, odd, odd. And my crossing or touching, since they're all odd, they all cross. And again, if I were to do a rough sketch of this, it's degree 5, so I know it ends like this. And it's going to cross at 0, -1, and 2. 0, -1, and 2. So it probably looks something like this, okay? And you can go on your graphic calculator to test it, but it's going to be pretty accurate. All right, try the last one on your own. All right, take about 20 seconds. Okay, so degree 2, and zeros are at 5 and -8. The multiplicity is odd and odd, because it's 1 and 1. And these are both crossing. And this is a parabola. You guys know this, so 8, 5, -40 is my y-intercept, which is -5 times 8. It's gonna look something like that, right? And this is something that you easily verifiable because we graphed parabolas, all right? Okay, so take a screenshot of this. This is important.
Mr. Bessler,
Yes.
can you just grow it up for 1 second?
Yeah. The whole thing, or is this good?
The whole thing, please.
Okay.
All right, thank you. I got it.
Okay. All right, so this is a summation of everything we've done so far. So the appearance of a polynomial function. The graph of a polynomial function is smooth, unbroken curve with no cusps or asymptotes. Okay, the asymptotes would mean now I have to take my pencil off, which we're not doing. Okay, the end behavior. The degree of the polynomial of the lead coefficient will be used to identify the end behavior. That's what we talked about with the power functions, right? X-intercepts, the real zeros. There are imaginary zeros. The number of x-intercepts will vary. The graph is in linear factored form. The x-intercepts is the opposite of the inside factor, right? That's what we did up here. That's why it was -2, it was +2, and it was +7, it was -7. If the graph's in standard form, use a calculator to approximate the zeros. We had to talk about that as a team. I don't think we're gonna be able to do that this year. Okay, so you guys got a break. The y-intercept, there's only one y-intercept. Let x equal 0 and solve for y. All right, behavior around the zeros. We decided definitely as a team that we're skipping this. Okay, so we're not gonna do this one around the zeros. It was kind of pointless even in regular times. Turning points. Okay, the number of turning points in the graph will be at most one less the degree of the polynomial. Okay, this is something new. So you guys, we say turning points, but you guys might call it humps. So for example, maybe a graph that we're somewhat familiar with. We know what cubics look like. And it's to the third power. And we know that cubics look like something like this. And if you look, it has 2 turning points. Because in order to find a turning points, it's 1 less than your degree. Now it said it has at most 1 less than. It could have no turning points if it's a really narrow graph. But the most it's going to have is 1 less than the degree. Because 3 minus 1 is 2. That's what it means for turning points. Increasing and decreasing. Use the x value of the turning points to determine whether the graph is increasing or decreasing. That's going to involve using the calculator. So we're going to have to figure that out because I know that not a lot of you guys are good with the calculator yet. It's just harder to do virtually. Domain, easy peasy. It's always all real numbers. And the range, when we talk about that, if it's an odd degree, it's all real numbers, right? So cubic to the 5th power, to the 7th power. If it's an even degree, you got to look at the graph to find the range, right? It's the biggest and lowest x value, y value. All right. So let's put our knowledge to the test here. Okay, so actually, these are the exact same problems. So let's just go ahead and go to example 7 because it has a graph there. All right, use a function to answer each question below. Find the x-intercepts, the y-intercepts. So the x-intercept is -4, 0, and 1, 0. The y-intercept, okay, I mean, you don't have to do it mentally, but you do have to put 0 in for x to solve for y. Remember, I don't want to see anybody say skip or IDK or leave it blank. No, you guys know this. You're seniors. The y-intercept is when x is equal to 0. It doesn't matter what the graph is. That's always the case. So -2 times 0 plus 4 squared times 0 minus 1 cubed. Now put the whole thing in your calculator. Okay. So -2 times 4 squared times -1 cubed, and you get 32. So 0, 32. All right, now multiplicity of the rightmost zero. This language could be a little confusing. So something that I think helps is if you just sketch X and Y, an XY plane here, and you put the points on there. So I know that -4, 0 is one of the points, and I know that 1, 0 is the other point. So when it says the rightmost zero, they're talking about the zero that's all the way to the right, which would be the number 1. And when they say the leftmost zero, they're talking about the zero that's all the way to the left, which would be -4. So now they want to know the multiplicity of the rightmost zero. Well, the multiplicity of 1, it's the number 3, or it's odd. And the multiplicity of the leftmost zero, well, that's 2, which is an even number. Okay, so that's what it means there when they say rightmost and leftmost. You're going to see that on Math Excel, so I want you guys to get used to that language. All right, now the graph crosses or touches X at the smallest X-intercept. Again, notation, language, all this matters. You've got to be strong readers in this class as well. So the smallest X-intercept is the same thing as saying the leftmost. And the leftmost is -4. So -4 has even, which means it touches, right? So smallest means the same thing as the left, and in this case, it's -4. The graph touches or crosses at the largest X-intercept. The largest is the rightmost, okay? All the way to the right, what's the biggest one to the right? And in this case, it's 1, and looking at 1, it has an odd multiplicity, which means it crosses. Now, what is a power function? In order to do that, you got to find a degree. And we have to use the lead coefficient. So the lead coefficient is -2, right? So sometimes there won't be a number there. So you know that's 1. It can't be 0. In this case, it has a number that's -2. And then the degree, I have to add 2 plus 3. So what is the power function? Well, it's going to be y equals -2x to the 5th. And now find the maximum number of turning points. Well, the maximum number of turning points is going to be 1 less than the degree. So that's 5 minus 1, which is 4. So this could have 4 humps. You won't know that unless you graph that. So our little trick of sketching only works on these intercepts, on the y, on the both x and y intercepts. But I can't tell the humps unless I officially graph it, right? But let's get a sketch and let's compare it to Desmos. Oh, I'm running out of time. All right, so -4, 0, 1, 0, 0, 32. It's negative, which means it's going down from left to right. And I know that it is going to touch here and cross here. So, you know, I'm taking a big chance. I haven't looked yet on Desmos, but it should look something like this with some humps in between. All right, so let's go to Desmos, see what this looks like. All right, so y equals -2 parentheses x plus 4 close parentheses, squared, parentheses, x minus 1, close parentheses, cubed. All right, not bad, right? I mean, this hump is way higher than what I had thought, but still, it goes through those points, and it's very narrow, right? So again, I didn't need a calculator to get the gist of what this graph looks like. I just used it based on my knowledge of crossing and touching, okay? That, I did not do at first block. So you guys got the star treatment there. All right, so using your calculator, I don't know, it's so tough. We're gonna skip for now. I gotta talk with our team. You know, I think it's just tough to do this, finding those points. Sorry, so it's not on the final for Eastern. So I think I'm okay with that. This, however, is. All right, so we're gonna work backwards here. This time now we have form a polynomial whose zeros and degree are given. So the zeros are -1, 1, and 8, and it's degree 3, which tells me that at the end of the day, it's going to be something to the x to the third power. It could be something in front of x, most likely not because I wasn't given a coefficient. But at the end of the day, it's going to be some x to the third power, right? And now what they want us to do is kind of work backwards. We're given the zeros, and the first thing we have to do is write out the factors. So the factors are going to be x plus 1, x minus 1, and x minus 8. Remember, it's just the opposite. Now, this is the part that, you know, it takes a little bit of time. I got to multiply out the factors. And then I got to rewrite it in descending order. Maybe. I learned some tricks in the day where you could kind of write it out without doing it right the first time, so you don't have to rearrange things. So looking at this, it seems like it's a lot of work. It's not really that much work, especially because with multiplication, you can rearrange the order and make it more convenient. The way it's written here is pretty convenient. X plus 1 times x minus 1. We know that that's a difference of squares. So that's just going to be x squared minus 1 times x minus 8. And now we multiply these two together. And like I said, you can do it so that you don't have to rewrite it if you do it right the first time. For example, I know that x times x squared is going to give me the biggest term. So that's going to be x cubed. And then x squared times -8 is -8x squared. -1 times x is -x, and -1 times -8 is +8. So I don't have to rearrange it. It's already in descending order. Okay, looking at B, this sometimes confuses students when they say that the 0 is 0. Well, if you think about it, x minus 0 is just x. So if I'm going to rewrite this in polynomial standard form, this is just going to be x times x minus 2 times x plus 5. And again, with multiplication, you could do it in any order, but it makes sense to do these two first because then I could just distribute x at the end, which is much easier. So g of x is equal to x times x squared plus 3x minus 10. And now I distribute the x to each term, and it's already going to be in descending order. G of x is equal to x cubed plus 3x squared minus 10x. All right. Last two things here. We'll do this one next class. We'll end here. We'll end with this. All right, the function defined by h of x is x to the fourth plus 5x cubed minus 48x squared minus 252x. Has the graph shown below. Okay, use the graph to factor the polynomial, right? So we're asking you to factor a quartic. Yes, oh, first page. Sorry, Claire, I just saw this. I'll go back to the first page. I'll scroll up. Okay, let me scroll up here.
No, I'm good now.
You good now? Okay. All right. So I know before you would never be able to factor this, but now we can because of our knowledge. So let's identify our zeros here. So this looks like it's at -6, 0. This is at 0, 0. And I knew that because of all the x's here. Every term has an x, so that's going to be one of them. And this one is 7, 0. Now, let's talk about other things we know about this. This is a touch. This is a cross. This is a cross. So that means this is even, this is odd, and this is odd. So if my zeros are -6, 0, and 7, even, odd, odd, what combinations of even and odd numbers can I add that's going to give me 4? Or in other words, we know that it's going to be x plus 6, x, and x minus 7. What we don't know is the exponents. But we have a good idea. We know it has to add up to 4, and we know that 2 of them have to be odd, and 1 of them has to be even. So what are these exponents going to be that when I add them together, I get 4?
1, 1, and 2.
1, 1, and 2. Perfect. So the x plus 6 has to be 2 because that's a touching 0. The x has to be a 1, and a 7 has to be a 1 because those are both crossing zeros. And now all I'm going to do is I'm going to rearrange it because typically we put x first. It doesn't have to be. It's not wrong if you don't do it, but to me, visually, it looks better. So in factored form, this equation is x times x plus 6 squared times x minus 7. There you have it. Okay. In the years past, you can only factor a quadratic. We just factored a quartic, but we needed a little help. We needed to have the graph to do this, and that's really going to be the goal of this unit is using the graph and using our knowledge of even and odd functions. We could factor any polynomial function. All right, so we will start this next class as a warm-up. I'll write this down. March 2nd, we're already in March. So March 2nd is the next time we meet. I'm gonna give you guys time now to upload it into Schoology. And remember, that's your ticket. So make sure you do it. I had to mark a kid absent already first block. I knew he was there, but he didn't turn it in, so I couldn't give it to him. All right, so I want everyone to submit it right now. And, you know, I'll give you guys time to submit it now, so we'll say our goodbyes now. Hold on. Oh, okay. Yeah, just turn in what you have now.